Hello there everybody, Sam's Trains here, welcome back to the railway. Today I'm going to be talking about one of my all-time favourite subjects, and that is, how do model trains actually work? A huge thank you to Wal and everybody else who suggested I do this video. I thought, yeah, that's a good idea, I'm going to do it. So I talk a lot in my reviews about mechanisms, right? What is good, what is bad, why this is better than that. And it takes me a hell of a long time to explain it, quite frankly. So I thought it would be really nice to do a video on model train mechanisms, define all of the different terms I use and talk about my perspective on what makes a good mechanism and what makes a bad mechanism, and in the process try to explain how everything works. So that is what I'm going to do today. I hope you enjoy it. I should say I'm going to be talking about HO scale, or gauge rather, HO or 00 gauge locomotives. Other scales may work in much the same way, but that's not guaranteed. Also, I'm going to be talking about model trains that pick up their power through the track, as the locos in my videos tend to do. There are lots of other approaches to this. You could have battery-powered trains that work via remote control. You can have clockwork trains, live steam locomotives, hey, even solar-powered trains if you watch my videos. But no, the locos in today's video are going to be the standard type that pick up power through the wheels. So now that that's all sorted, let's get on to part one, and that is, of course, picking up power. Obviously, without power, your model trains won't work. The motors won't work, you won't get any sound, you won't get any lights. So it's really important that you establish a good solid connection to the track in order for the model to work properly. And there are two main ways of picking up power from the tracks, either through the wheels or through the axles. Now, to pick up through the wheels, you tend to just have a copper wiper like this one, which touches part of the wheel, which is usually the inner flange. To pick up through the axles, you have to have a conductive axle, of course, like this one perhaps. You might have a copper wire touching the axle, although it's more normal to have conductive bearings, as you can see on these Bachmann split chassis locomotives. And even though the Bachmann split chassis locos are quite old and outdated, you do see more modern locos using this technique. For example, this Dapol Class 73 actually does pick up through the axles. Now, it sounds like these two approaches might be very similar to each other, but actually they're not. They're quite a bit different. So let's talk about some of these differences. So first of all, when you're picking up through the wheels, obviously only the outer tyre of the wheel needs to be metal or conductive, and that is the case with lots of Hornby locomotives. As you can see here, it is just the metal tyre that's made of metal. The rest of the wheel can be plastic, and I can show you this on a diagram. So there's a little key in the bottom left there to show you what's conductive and what's not. This is the simplest way of doing things. Now, picking up through the axles is a bit more complicated because clearly you need to get the power from the surface of the wheel that touches the track to the axle itself. And to do this, usually the entire wheel is made of metal, or at least part of an entire wheel is made of metal, in order to conduct electricity to the axle. However, if both wheels are connected to the same axle, if you look at this diagram here, you can see that there's going to be a short circuit. You're connecting the left rail and the right rail together, which will obviously blow up your controller. So it's necessary to have some sort of break in that axle. We need to bisect the axle with an insulator so that the two halves don't short together. Now, just to throw something interesting in here, some locomotives pick up through both the wheels and through the axles. A good example is Triang locomotives. These actually do both. So Triang wheels are all made of metal, but only wheels on one side of the model are allowed to conduct to the axle. The other one has a plastic insulator, something like this. And now in this diagram, it is the left wheel that conducts through the axle to the chassis, as you can see there. So that left wheel is live to the axle. The right wheel is insulated from the axle and has a copper pickup. And if I'll show you a Triang locomotive, you can see this in action. So that is how the Triang locos used to work. Both of these approaches then have advantages and disadvantages. Here are a few of them. So picking up through the wheels using a wiper pickup, that is pretty simple. It's simple to manufacture. It's also a lot better for servicing and maintenance. Most of the time you can pull those pickups away like this, and then you've got full access to the axles. There's nothing in your way there. It's also a fairly reliable way of picking up power, so most manufacturers do tend to opt for this. There are some disadvantages to using wiper pickups though. First of all, they can be visible. Now, most clever manufacturers, and I do emphasize that, they might paint them black so they're not so noticeable, or they might position them in a sensible place so that they're not visible, but that's not always the case. Second of all, the wiper pickups can be quite fragile. If you accidentally bend one of them, they can not work. So that is something to bear in mind. Also, after hours and hours and hours and hours, and probably days and days and days of running, those wiper pickups are liable to wear away as well. So do bear that in mind, although I very rarely see that. It's only sort of the really old 60-year-old trying locomotives that do actually wear their pickups away, but it can happen, so bear that in mind. Right, picking up through the axles then, let's have some pros for these. Well, first of all, they're absolutely invisible. There's no pickups on display from the outside of the model. There's also usually a larger electrical contact area, which allows better conductivity. And finally, this approach produces less friction in the mechanism because obviously wiper pickups touching the wheels will cause a little bit of drag. Well, a locomotive has to have bearings, so if the picking up is done through the bearings, then there will be less friction there, which makes sense. There are quite a lot of cons with this approach, in fact, an awful lot of cons. First of all, in many cases, these models are much more difficult to disassemble to get access to the axles for cleaning and such. Some of those DJM locomotives make this very, very difficult indeed. Therefore, the locomotives can become less reliable over time. Also, some lubricants can cause problems as well because many lubricants are not conductive. So if you cover a locomotive axle that needs to conduct in, let's say, sewing machine oil, that can act as an insulator and stop the model working properly. And the final and most devastating disadvantage to this approach comes from the fact that we have to have a plastic insulator between the two halves of the axle, because that is a point of failure. Plastic is weak, of course, and in many cases, particularly the Bachmann split chassis locomotives, that plastic insulator in the middle can crack, break, it can cause the locomotive to lose gauge, and in some cases it can just cause the locomotive wheels to break apart, thus ruining the locomotive. So that leads us nicely on to part 2, which I'm going to call powering your models. So at this point we've figured out how we're going to pick up power from the tracks, and we've got 2 wires with that power ready to go. Now in the old days those wires would usually connect directly to a motor. Here's an old Lima diesel. You can see the wires literally connect straight up to the motor. On modern locomotives that isn't the case. Those wires instead connect to something called a DCC socket. And yes, that is the case even if you don't have a decoder fitted into your locomotive. If you want to learn more about DCC, I do have a video up here, so check that out if you like. And these DCC sockets serve to distribute power to every aspect of the model, whether that be lights, sound, other functions, or obviously the motors. And motors is something we're going to come to right now. There are lots and lots of types of motors and specific motors, there are hundreds of them, but I'm going to talk about just the 3 main types. So the first type is the 3-pole brushed DC motor, second type is the 5-pole brushed DC motor, and the third type is coreless motors. I'm going to talk a bit about those right now. So let's first talk about 3-pole motors. Now this is one of them here. This is the cheapest and most common type of motor, and it tends to be used in cheaper lower end models, although some naughty manufacturers put them in super expensive high end models, which is a bit nonsensical, but that's what they do. They're called 3-pole because they consist of 3 coils of wire, which are also known as rotor coils. Then you have these conductive brushes which deliver power to these plates, which are known as the commutator. So when a current passes through these coils of wire, that induces a magnetic field which interacts with another magnetic field caused by a permanent magnet. All of these motors have a permanent magnet inside, and that is of course what produces the rotation. Now on a 3-pole motor, one rotation of the motor armature is split up into 3 pulses of power. A 5-pole motor splits up that one rotation into 5 pulses of power, and as you can imagine that offers greater torque at slow speed, and it also reduces the chance of a locomotive stalling. Now both 3 and 5-pole motors are known for an effect called cogging. Now this isn't always noticeable, but because the rotation of a motor is split into pulses rather than one smooth motion, that jerkiness can sometimes show through in the performance of a locomotive, and to combat that manufacturers use flywheels. Now this is a flywheel here, as you can see it's just a big heavy piece of metal which is attached to the armature. Now the way this works is that energy is transferred from the armature to that heavy spinning flywheel during a pulse of power, and then when the pulse is finished that flywheel is able to transfer some of that energy back into the armature and keep it spinning smoothly, and that is the basic idea of flywheels. Also, if the flywheel is large enough like this one, they're actually able to maintain the speed of a locomotive even when the power is cut out for an extended period, for example over points. So flywheels are a really nice feature, and that's why manufacturers use them. But yes, without a flywheel, a 5-pole motor will produce less cogging than a 3-pole motor. However, 5-pole motors are obviously more expensive to produce because you've got 5 coils of wire and not 3, and they're also more prone to overheating if they're not designed efficiently, because obviously current passing through a wire does produce heat. Now, speaking of efficiency, you might often hear the term skew wound thrown around. Now, skew wound armatures work exactly the same, except the coils of wire are wound in a slightly different way. They're sort of twisted a bit like a screw thread, which produces a smoother rotation, which obviously is quite important for slow speed. Now then, let's move on to coreless motors. This is something that people ask me a lot. So this is a coreless motor, and first of all I'm going to clear up a couple of misconceptions. So misconception number 1, coreless motors don't have brushes. That is incorrect. Coreless motors usually, at least the ones in model railways, they do have brushes. People that say they don't have brushes, I think, are getting them confused with brushless motors, and they work very, very differently. I've never seen a brushless motor in a model train because they're quite complicated. They require quite a bit of circuitry to make them work. Just forget about brushless motors in model railways. Maybe in larger gauges they will be used, but in 00 or HO scale I've never seen one. If you have though, let me know down in the comments. Secondly, I've heard people say that there's no rotating armature inside and the coils are static. Yeah, again, as far as I know, that is not true. You still have a rotating armature. It just works a little bit different. So I'm going to read out a little bit of info on coreless motors. So the key difference between standard motors and coreless motors is that coreless motors do not have an iron core around which the wire is wound. So there's actually nothing holding the windings in a coreless motor. They're really efficiently wound to be self-supporting, and the whole thing rotates inside a magnetic housing, and so the armature is actually really lightweight. They're incredibly light, in fact. Now, there are some pros and cons of coreless motors. Here are some of the pros. So generally they're smaller and lighter than motors that have a heavy iron core on the inside. I guess that makes sense. They're relatively cheap because there's no iron core, although they're not dirt cheap because the way these coils are wound is quite complicated. These motors are very efficient and they last quite a long time because there's quite low inductance in these windings, which produces less sparking and arcing around the brushes, which makes the brushes last longer. And the lack of iron core also produces a smoother rotation as well. So sometimes you will see that coreless motors are not fitted with flywheels, and that might be why, because there's less cogging on a coreless motor. There are quite a few cons with coreless motors as well though. First of all, because of how light the armatures are for not having the iron core, these motors are really good for acceleration. They can accelerate really suddenly. Now in model aircraft that is a pro, but it doesn't really apply to model railways. There's no real need to suddenly accelerate model trains, so that is not really a con, but it's not a pro either. It is an advantage of coreless motors, but it's not an advantage that works in the favour of model railways, so that one's a bit of a silly one. So you can see a bit of erratic control as a result. You also have problems with feedback controllers. Now, I'm not going to get into feedback controllers today. I think that would have to be another video, but coreless motors behave differently to traditional motors, and therefore controllers designed with feedback functionality can get confused by a coreless motor, and it can damage either the motor or the controller, which is obviously not a good idea. Now, the final con with coreless motors again comes from the fact that there is no iron core. Motors that have iron cores can dissipate heat quite effectively because those iron cores absorb lots of heat. Well, obviously a coreless motor has no iron core, and so it's much more difficult to dissipate that heat, which means coreless motors are prone to overheating. Now, I've never known this be a problem on a smaller locomotive where there's not much power involved. I've actually never seen a coreless motor used in something larger. However, a larger locomotive that might be asked to do a lot of work, or perhaps one that has traction tyres fitted so that it can do a lot of work if needed, yeah, there is a risk that those coreless motors could overheat and damage themselves. But weighing up all the pros and cons, I would say that, yeah, a traditional 5-pole motor would be my choice. So let's move on to part 3 then. I'm going to call part 3 transmission. So we've got power to our locomotive and we've got a motor that is spinning, but obviously the wheels aren't going anywhere right now. So we need some way of getting power from that motor to the wheels. Now, some manufacturers opt for bizarre solutions. I've seen belt drives on some locomotives. Other weird things may exist as well. However, that is not the way that most manufacturers choose to go. Most of the time we have some sort of gearing between the motor and the armature. Now, the gears actually serve two purposes. First of all, they transfer energy from the motor to the wheels, because obviously the motor and the wheels are not normally in the same place, but they also act to reduce the speed of the motor so that the wheels aren't running too fast, because a motor spins really fast and you don't want the wheels to be going that quick. So some sort of reduction is needed. This is done with a worm drive. Usually you will have some sort of worm drive connected to the motor shaft because the form factor of a locomotive makes that necessary. Locomotives are long and thin, and so is a worm drive, so that makes sense. It doesn't look like it, but worm drives actually do quite a bit of the speed reduction. It's not quite as obvious as looking at small and large gears, but they do that. Diesels also use worm drives, although those worm drives are not normally connected directly to the motor. You've usually got drive shafts extending from both ends of the motor, which connect to worm gears on each bogie. And then from there, the way a diesel and a steam locomotive works is quite similar. You've got a train of gears usually, it's called the gear train, and those descend from the worm drive, small to large usually, although the ratio may be 1:1 if the worm drive has done all the reduction required. This reduces the speed down nicely so that the wheels turn at a nice sensible speed. Now on a steam locomotive, usually you just have one driving axle. Only one axle has a gear fitted to it. The rest of the wheels actually turn the way that a real locomotive wheels would turn. That is via the coupling rods which connect, or couple rather, all of the wheels together. So that's how that works. Some steam locomotives don't work like this. Again, sillier manufacturers like DJM, they might decide to drive every single axle with a gear, which is obviously noisier and causes more friction. I'm not a fan of this approach. It makes the coupling rods useless, and there are no advantages. In fact, there's just disadvantages: more noise, more cost. Yeah, not a good idea, I don't think. In diesels though, there is obviously no choice to drive all of the axles because there are no coupling rods to help with that. So the axles are either all geared individually, or sometimes one or two axles will be missed out. But for the most part, the best quality diesels have all axles driven. Although that's not always the case on some cheaper models like the Hornby Railroad diesels, for example. Only one bogie will be driven, the other one will do nothing besides pick up power. Okay, so we now have a working locomotive. Our model picks up power, it's got a motor of our choice inside, and there's a gear train which connects the motor to the wheel set. However, that is not all that's needed to make a model train work. We've ignored friction. Now, there are lots of opportunities in a model train to lose energy from the motor due to friction. There are motor bearings which waste energy. Every single gear shaft that turns is touching the chassis and wasting energy. You've got gears rubbing against each other, that wastes energy. Axles rubbing against the chassis. You've got valve gear that moves and produces drag, pickup wipers that touch the wheels and produce drag as well. That means there's a lot of power that's coming out of the motor, but it's not being used to turn the locomotive wheels, it's being used to overcome all the friction in the system. And so manufacturers use lots of different techniques to reduce friction in the drive mechanisms and improve performance. The most basic one is of course lubricant. You've seen the gloopy stuff on the gears of your model trains. Yep, that's lubricant, that reduces the friction. And you've got lighter oil as well, which is less easy to see on the motor bearings, for example, or on the valve gear. Good manufacturers will use proper turned brass bearings on the axles of the locomotives as well. Now, these are machined to be much smoother than just sort of cast bearings that you might find just moulded into the chassis. That's what Bachmann do quite often. It is cheap, but it doesn't produce the best performance. No, the best performing models do have proper turned metal bearings. Some people have tried to convince me that proper metal bearings don't really matter and they shouldn't be done. Well, I don't agree with you, and it seems that the manufacturers don't agree with you either, because basically every new model that comes out does have the proper bearings fitted now, and that goes for Bachmann as well. So I would ask, if Bachmann didn't see the advantage of fitting proper metal bearings, why are they now doing it on all of their models? They do make a difference. Some manufacturers might even go the extra mile and even put bearings on the gear shafts, and this is an extra nice touch. This is very rare. Hornby did this a few times. I don't think they tend to do it anymore, but that is extra nice, and I just thought I would throw that in there. They might also use conductive lubricant on the wiper pickups. Now, this means that they can still conduct. It's important that you don't just put regular lubricant onto those because that will insulate them and make the wheels dirty. But the right stuff can actually go a long way to reduce drag and maintain the conductivity of the pickups. So there you go, that's a little bit about friction and what the manufacturers can do to avoid it. Finally then, let's talk about pulling power, because maybe our locomotive is working really nicely without friction, but it's not able to pull very much. Why is that? Well, it comes down to friction. We've been trying to get rid of friction in every area of the locomotive, but there's one place that you do want friction, and that is of course between the wheels and the rails. And it's this friction that gives the locomotive pulling power, or rather tractive effort as it's also known. It's all very well to have wheels turning around with as much power as you like, but if those wheels are not gripping the track and the locomotive's not going anywhere, then obviously that is useless. And there are three main methods that manufacturers use to improve the tractive effort of their models. The first one is to make the locomotive heavier. This is my favourite. So you might see die-cast bodies on a locomotive, die-cast running plates. The chassis might be adorned with extra weights and stuff, because the more weight a locomotive has, the more grip it will have on the track. Another approach is to increase the number of driving wheels. For example, these days a diesel might have every single one of its axles driven, whereas back in the 1950s or the 1960s you'd be lucky to have maybe 2 out of 6 axles driven. Obviously that is finite though, because let's say an 040 steam locomotive cannot possibly have any more than 2 driven axles, and that is where the third and more dubious approach comes in, and I'm sure you can guess what that might be. Yes, of course, that is changing the material of the wheels to one that has a higher coefficient of friction. Now that isn't just a posh convoluted way of saying a manufacturer uses rubber traction tyres. They do that obviously, as we know, but there are also other metals that wheels can be made of that increase friction. I'm not sure what those might be, but I have seen it quite a lot on the different models I've reviewed. Different metals do seem to work better than others at gripping the track. And yes, sometimes that does involve rubber traction tyres, which I'm not very keen on. However, they do work, they do increase the pulling power of a locomotive. However, I'm not going to talk about those today, so if you want to find out more about traction tyres, there is a video right there. Anyway, I think that is the basics. There are other things I could have talked about in this video. If there's anything in particular you'd be interested to learn more about, but I didn't talk about it today, do comment down below and let me know what that is. But hopefully that will be interesting for you. Hopefully you learnt a little bit about locomotive mechanisms, and hopefully some of my comments in my various reviews and such make sense now, make more sense than perhaps they did before. Yeah, that was good fun actually. It was nice just to open up some locos and show their innards, to be honest. So thank you so much for watching. Let me know down in the comments what you thought about the video, and I will see you very soon for some more reviews. Alright, you take care of yourself folks. See you soon.